Hi, my name is Edward Zhang, and today I'm going to be presenting the paper MiniLLM Knowledge Distillation of Large Language Models. To preface, the paper covers two main concepts: first, a general framework of distilling LLMs, and then a corresponding reinforcement learning policy grading algorithm for specific teacher-student interactions. My research extension focuses on the first aspect, so I'll be covering that mostly. The motivation behind the concept of knowledge distillation in LLMs is a couplefold. First, the rapid development of LLMs has led to rising parameter counts, and because of scaling laws, this has also led to larger pools of requisite data needed to train and also higher computational costs. Knowledge distillation is a strategy that has been commonly used to reduce these constraints on knowledge acquisition, and other strategies like quantization has been proposed, but can only go so far. What is distillation? Distillation, put simply, is a form of compression or training technique where a large complex model or a teacher model is used to train a smaller, more compact model, also known as the student model. The teacher and student models may vary in architecture and size, but at the core, the student model learns by replicating the performance of the teacher model by looking at the output distribution of the teacher model and emulating it. The authors of MiniLLM highlight two types of distillation. First is black box KD, where you only have the teacher-generated texts as the inputs. And so these are like prompt response pairs generated by LLM APIs. The second paradigm is white box KD. These approaches are mostly studied for smaller, have been mostly studied for smaller, like sub 1 billion parameter models, and have yet to be explored more. But white box KD is where when you have the teacher model's output distribution or intermediate hidden states also available, so that you can compare and do some optimizations based off that. So to give an example, we have this diagram where we have training data. Normally training data is fed into a model. You have some output of the model and you have some ground truth, and then you find some loss function based off of the ground truth and the output. But for distillation, what you do is you have a student model denoted p theta, where theta is the learnable parameters, and then you also have this teacher model denoted p. And so for the teacher model, p is frozen, and you have the student model, so q theta is running, and the loss function, instead of looking at the ground truth loss, we run data through the teacher and the student model. We look at the soft distributions, the soft targets, so this can be like post-soft softmax logics, or like the actual values inside the intention layers for transformers. We can compare this, and it's a much better because it's much more it has much more granular information about actual knowledge, and it's a much more token efficient way to train. Here's a kind of a toy example. So we have the sequence, the sun rose. So we have the word the getting passed into the teacher and student model. You have some output distribution where the teacher correctly predicts the next word, which is sun. The student incorrectly predicts the next word, which is rose. And you have these two distributions, and you want to have some sort of metric to compare them. And so to make it so that the student model emulates the teacher model distribution. And the way that you do this is by using KL divergence, which is a measure of like the distance between two different probability functions, distributions. And so you have the ratio of the p and q theta log transform multiplied by the individual probabilities to get KL divergence. So let's talk about the MiniLLM method. The authors of MiniLLM kind of use reverse KL divergence. So in regular distillation, you use forward KL divergence to compare the distributions. However, the LLM authors say that it's a bad way to do distillation and propose a new method. For previous forward KL divergence distillation, you have text classification and like vision classification. And so these are great examples that actually work, because the output space usually consists of a finite number of classes, such that both the student and teacher model distributions have a few modes. But for open-ended text generation tasks, which is usually the case of LLM applications, the output spaces are much more complex, and the teacher distribution can contain many more nodes than what the student distribution can express due to limited model capacity size. So let's say the student model is 1 billion parameters and the teacher model is 10 billion parameters. The student model may have a hard time because it has fewer parameters, and you can run into optimization issues. Minimizing forward KL divergence causes the student model to assign unreasonably high probabilities to the void regions of the distribution, and can lead to mean seeking, which forces the student to match the mean values of the teacher model. So if you look at the graph that the MiniLLM authors provided, you have the solid blue line, which is the target distribution, so the teacher distribution, and then you have forward KL divergence, which is indicated by the orange dotted line. So it doesn't do really well either modes, but you have reverse KL divergence, which doesn't do that well on the lower left, these smaller modes, but does well on the higher modes. And that's fine, because for like sampling and next token prediction, what you really care about is just the highest value, the highest mode anyways. So it does a much better job at what it needs to be doing. And so next, we have a kind of results spreadsheet that the authors provide. And so they use this reverse KL divergence process and distilled over a couple billion tokens on different model sizes. And they found that the student model reaches as good performance as the teacher model, and at some cases, even beats the teacher model. For my replication, I use the teacher and student model. Both are the same size. I use Qwen 2.5 coder, 1.3 billion parameters. 1.5 billion parameters, and I distilled my randomly initialized student model for 2 billion tokens, and the performance is almost as good as the teacher model, which has been trained on 7 trillion tokens. Here are my references, and thank you so much for listening.